question. Both the graduate position. Well, they're gonna get my charger back because someone took it. They're just not gonna give whoever took mine original. I know, but someone had to take it for it to not be there anymore. No, I left it in Mr. A's room. Yeah. And someone took it. Like the second week of school. So they didn't know. Bro, like it took me a while to remember that. Because I thought I just lost it, but then I was like, I actually left it plugged up. And he didn't have it.
Yeah. So what are that's soon.
I'm really excited that 12th? The 12th?
March 12th, yes, March
It's
12th.
the 25th.
I understand. So where we voted to nominate a court.
So what's gonna happen is next week on Monday, the seniors will vote on cohort A, and the next Thursday, the seniors will vote cohort B.
During the email, then why wouldn't it just all be on Monday?
Because that's what I said, so you get this moving along, you know, say that.
Yeah, how did you supposed to find the birds in a week?
I wanted to wear my Nike shorts today, but my family said I couldn't.
I wore Nike shorts last 3 days because it feels so good outside.
I know like that.
Mine are filthy.
But, and then we're gonna do like a video for the student body before they vote of all the people on the court saying, hey, I'm this, and then we're gonna do like, we're just gonna have like funny questions that you have to answer in the video, so it's not just like, hey, I'm Kelly Payne, I'm a senior. Just so it's not stupid like that. But, and then we can't, I don't think we can be on the field yet, they'll wait and see if it changes, but we're gonna,
Like on the track.
on the track and stuff.
I'm trying to be on the field. It's not like the grass is gonna be growing. Right? What?
I don't know, we're trying to figure out, cause like stuff keeps changing, so we're trying to like, cause me and Mary came up with a whole plan last week of how to do it before the game, and like, the schedule, like the times and everything, and it's just. I hate riding with this.
So how did you do it?
So I was going down the hill, and it's such like this way. I'm going down backwards, trying to slow myself down so my toes are in. And I think I let up on my toes too early, and so the back of my board, like, hitched on the snow, flipped.
When you go frontwards.
I flipped and then fell frontwards. And this problem.
Ooh.
Yeah.
I like snowboard better than skiing because I can just, like, when I'm skiing, like, I cannot slow down.
I've never skied, I've only ever
And it's
snowboarded.
scary. Like, snowboarding, I feel like it's so much easier because I just stay, like, sideways hold on.
Jordan did both. Jordan did both, and Jordan could not snowboard. It
I'm
was
so
so
facing
funny.
down the hill the whole time.
This one time, I was going up the hill, and I was watching Jordan, and she's on the cover, and she goes, just like face into the snow. It was so
I
funny.
started going and I was like, video and put on my Instagram story. And like, so I wasn't looking at my feet. I was looking at my phone, I was like, and then like all of a sudden I hit like this bump and I was like, and like I fell straight forward on my face and like getting off the breath. I was sitting there. But yeah, I'm like screaming.
Huh?
It's like not come fresh out.
That's only
Like, so
questions.
it just made it come out. Yeah, I'm in center. And this guy was like looking, he's like, are you okay?
I was in there, I was holding the whole time though.
Like it like blacked out like it would come back on. I thought I heard it. I think I'm just going.
Well, I was helping Carly get up one time, and this kid was on his skis, and I mean, we were on the bunny hill because like Carly was learning how to do it, and I was like, hey, what's up? And this kid comes flying, like, bigger than me, kid comes flying down on the skis, and he goes past me, hits me with a ski pole, and then goes through the entire, like, roped off waiting area for the, like, right conveyor.
Yeah, and like the first time we were going to speed race, he did that. She got like stuck there beside it, and I had to like pull her back up.
Well, my dad was on his skis, like, over the side, and he didn't even care that, like, he almost took me out. He was over there doubled over crying. That's funny. Clarence Cooper was not good at it, and it brought me so much joy.
Basically, she's like,
Well, because it was like, they did better than me to start out with, but then, like, I figured out, like, how to do it, and then I was doing it, because, like, at the beginning, I sucked at it. But,
Hello. My God, Colin, you do exist. I haven't seen you in a decade, it feels like. How's everybody doing today?
okay.
Good. We are going to start Unit 4 today. Now, I do believe I got some homework to collect from you all, so let's go ahead, let's get that out, let's get that ready. While we wait for our fellow classmates to log in. No, it's just the last night. That's right. That 10,001 assignments rolling around in my brain right now.
What I'll do next, and I'll
I need 3.5, 3.6, 3.7, 3.9, and you can do the chicken dance.
That's the 5.
Yeah.
6. 7. Yeah.
It's the EPA on recovery.
So they think that I sprained that, like, middle joint, so that's like 8 to 10 weeks if that's what they think. And then, they couldn't tell on the, x-rays when we went, so it was really swollen. But they think I might have cracked like some of the small bones, like.
It's something that it's.
Yeah, I hope it's like just this
So you
one.
can get out there.
Yeah, I hope so too. Huh?
I bet that hurt.
They were like,
Did you just snowboard this all the way down the mountain after?
no, like it was our last one. It was like 9:45, and so we were gonna come down, and they just taken the sign out of the middle so I could go straight down. Because I kept on between the signs, so I was just like falling forward. But so I was so excited, and so I went, and then it happened, and I just like laid in and I put my face right on it. She didn't have a very low baseline. So then I felt really lightheaded, and then I felt like and then I let it about 2 minutes and I sat up, and I was like, okay, like, can I play? I think I can get up. So I flipped over on my knees and I put my hand down, I put my hand down, and was getting ready to push myself up, and then I put some snow on it and just sat it for a minute, and it felt fine. So then, and then when I put weight on it, I like fell down. I was like, nope. Like sober up, fell right down. It's not very nice.
That's just good.
Yeah, I mean, honestly, we're just talking about.
Wait, so we're voting Monday or Thursday, and we have that Watson?
I'm probably going Friday. Because if we can get everyone voted by second period on Thursday, then I can count them up when I leave. Like when I get
You have
home.
to count it?
Huh?
You have to count them, does the computer know?
Just, not count them, just double check everything, make sure.
Oh my God, Tyler. Okay, so next Friday is the 5th, so it's week 2. And then the 12th is the next Friday.
And then we were supposed to be able to do stuff this week, and then, Mr. Johnson couldn't be this week.
So that
Until
week,
tomorrow.
of the 8th through the 12th, are we gonna do like a spirit week?
That's what we're talking about tomorrow.
You know, overall's at Christmas.
I know. So tomorrow,
We can do that on
we have to do that.
Well, we can do it on Sunday. I don't know, actually. because-
Next week, next Friday is the South Point game.
What?
Next Friday is the South Point game. And then
That's the
our,
first one.
no, the first football game is tomorrow, but it's away to Shelby. Then
Why would
it's
it be
South
so
Point.
early?
Huh?
Why would it be so early?
Football? So we can get baseball and everything else.
I'm saying like the homecoming, why are we on the first weekend?
Cause that's, it's the second game. Next week is South Point, and then the next week, which is homecoming, will be ours.
Oh. I mean, not next week, or next week, but the week.
All right, guys and gals,
We're gonna try to.
I don't know who we do.
let's go ahead. Let's get started. Do we have any homework questions? 3739, study guide? Anything we want to talk about today? If things go according to plan and things go quickly, we can dismiss the live stream early and spend some time outside doing some math problems today, because it is really nice out and we're all dressed reasonably appropriate.
Can we do, 7 from 3.9?
7 on 3.9. Have to look and see if I can track down another one of those sheets somewhere, but I believe we will be able to do it.
Yeah, we do open up. Thank you.
Here. Three dot nine and number 9. Oh yeah, this is a good one.
Oh.
You said.
Oh no, you said number 7, not number
But
9.
we do number 9 too.
We'll take a look at both. How about that? We'll take a look at both. Number 9 and number 7 from our 3.9 work. Okay, so let's start with number 7. Number 7, we have the linear approximation for this function at x equals 0. And they've given us a estimate the value of negative 1/10. Estimate the value of negative 1/10. So, of course, what we're going to need to start with is we're going to need to start with this function here. We have 1 over, why did I make that so small? 1 over 2 plus sine of x over 2. We have y equal to 1 over 2 plus sine of x over 2. Are we all okay so far? Okay, so the first step here is to do what? First step here is to do what? How do we do linear approximation? What's the first thing we need to do?
Find the derivative.
Find the derivative. That's a great place to start. How do we want to start the derivative? How do we want to start the derivative? Here's my answer key. Look what I've done. First thing I did was I rewrote this. So that way it's all one nice neat clean. 2 plus sine of x over 2 to the negative 1. That's what I did to start, because I think it'd be a lot easier to not have to do a quotient rule here. So for me to not have to do that, I'm just going to go ahead and take this, put it to a negative exponent. From this point, it should just be a chain rule. It should be a chain rule. So when we set up the first derivative here, the negative 1, of course, is going to come down. 2 plus sine of x over 2 to the negative second now. Agreed? We see that there in the first spot. Okay, the derivative of what's inside, that's going to be 0 plus, we'll have cosine of x over 2. That's the derivative of the first interior. Now we need to go to the interior again, the interior of cosine of x over 2, which is, of course, just going to be 1 over 2 or 1/2. So that's where I gained all of those multipliers from. Are we okay with this? Okay? You can unstack it or you can rearrange it how you like. I would probably go with negative cosine x over 2 times 2 plus sine x over 2 quantity squared. This is, of course, our derivative function. It's our derivative function. What are we going to do with it now that we have it? What's the next step in linear approximations? We actually skipped over the first step, but that's okay. We can go back and get it if we want. What do we need to do now that I have the derivative? Our absolute silence is concerning. We're going to plug in the x. The x value that we're interested in, or we have right now, is 0, right? We will be estimating our 1/10. So when we get to this point eventually, we're going to have y minus y1 mx minus x1. What we have here is we already have our negative 1/10, and we already have minus 0, correct? So we're trying to fill in these ones here. This is what we'll be looking for, is that y. So let's plug in our 0 here. So this is negative cosine of 0, right? 0 over 2, 0. Over 2 plus sine of 0, quantity squared. Agreed? We okay with how I substituted in? I reduced, of course, over 2 because we don't need that. Cosine of 0 is what? Jake?
1.
1. Thank you, sir. So we're looking at negative 1 on top. 2 plus sine of 0 is 0. Quantity squared. So we're looking at negative 1 over 2 squared. We're looking at negative 1/8 as our slope here. Negative 1/8 as our slope here. Are we okay with this so far? This is where we're at now on my answer key right here. Okay, that can go in. What else do we need? What did we forget to do at the beginning? y1, which of course we're just going to plug 0 into this equation. One over 2 plus sine of 0, which of course is 1/2, right? So that is our y1. We have our tangent line approximation ready to be evaluated and simplified down. That is the next step, of course, in my answer key there. And everything reduces down. Everything will reduce down. We're going to get 1/2. This is going to become 1 over 80. And we'll add that 1/2 over. So this is 1 over 80 plus 40 over 80, which is 1/2. So we got 41 over 80. Or whatever decimal you'd like for that. Questions? Okay. And we're going to talk briefly about number 9. Number 9 with that table. Number 9 with that table. See if I can find it here. Go. Number 9 with this table. I like this problem because it's done the first and derivative test, first and second derivative test for you at different points and different values. You have to be able to read and interpret what this table readout is telling you. What this table readout is telling you. So of course, across the top here, we have our standard x values. Across the bottom, we have our standard derivative values as we're going. So if we want to do a tangent line approximation for at 1.2, we'd be looking over here between 1 and 1.5. Probably use 1 because it is closer. So you can set up and solve that down. That's what they want us to do. What they've done is they've done all of this work already for us. They did all of this, and they're just giving us just these values now to plug in. That's what they want us to do here. So when I look at this, when it says write the equation for the tangent line for x equal 1, I'm going to ignore everything else on my table except for where we're at 1.0. So I know there that my x1 will be 1. I know my y1 is -4. And I know my slope, my m, is going to be +5. And then it asked me to predict at 1.2. So I'll plug in 1.2 for my x. And then what we want to know is this going to be an overestimation or an underestimation? How would we know that? How could we know that?
It tells you that your second derivative is greater than 0.
My second derivative is greater than 0, yes, which tells me what, Bianca?
That your tangent line is an underestimation.
We are going to be concave up, and we talked about when we are concave up, we are underestimating because we're skimming off the bottom of that curve, right? As opposed to the top of it when it's concave down. Questions here? I like that question. I really do because it gives you a ton of excess information. You don't need that whole table. That whole table there is simply just to distract you and try to make you think it is harder than what it should be. You have all the information you need. It's actually much simpler than this question. The only part of it that is difficult to understand or might push you a little bit farther is it going to be an overestimation and underestimation? Which if you go back through your notes, you saw right at the top, you guys, I think here specifically were here for that lesson, weren't you? That was like the only thing I taught live last week, I'm pretty sure. So you should have that physical paper that has the notes up at the top that talks about concavity, which is our second derivative. Questions here? Yeah, I like number 9 because it's actually a very easy question if you know what you're doing. If you don't know what you're doing, well, you're stuck. Any other questions here? Homework, study guide, anything else related? Okay then. Today we are going to launch 4.1. Today we are going to launch our lesson for 4.1. Yes, miss.
You haven't published Unit 4 for us yet?
I did not publish it. Crap. I swear I did. Let's go double check the modules. Bianca is right as always. Of course. Of course. Stupid Mr. Thompson. Get your act together. Let's check our live stream here. Okay. It should be up now. You should be able to click on it now. I keep forgetting to do that because I publish the individual page, but I forget to publish the whole unit. I do apologize. So we're going to start 4.1 today, which is anti-differentiation, also known as integrals, also known as integration or integrals. So just like with everything else in the world of mathematics, you have an operation, adding and subtracting. You have multiplying and dividing. You have exponents and roots, right? So in calculus, you have derivatives. Its counterpart is the integral. So if we have struggled with doing derivatives, if we weren't up on that and we've struggled with getting those correct, today can be a day that helps rectify all that. Because we're going to be doing all the same rules, but we are going to be applying them backwards, in reverse. Okay? So let's go ahead. Let's get started. Let's move into our second slide here with some actual notes. This is our homework. I've been moving those slides to the front because Mr. Kaufman sometimes forgets to show it. So our second slide is actually our homework. You want to jot that down, you can. Of course, it's right there on Canvas for you as well, now that we have everything published and ready to go. So let's actually go on to slide 3 where our notes are really going to begin. So anti-differentiation. We are going to start looking at the derivatives, and we are going to start using the rules in reverse to state what the original function is going to be. So we're going to be taking and looking at y derivative, or first derivative of fx, dy dx, and we are going to be going back to y. We do not typically use function notation for this. We either use dy over dx, or we use y prime notations for this. And we'll talk about why we don't use function notation. Let's talk about why we don't use function notation. Why are we not going to use f of x here? So, moving on to slide 4. Here's my question. Which one of these would apply for the function f of x? If we were going to do the power rule in reverse, if that's my first derivative up there of fx, right? F of x. Let's think about the power rule in reverse. That means the coefficient used to be the exponent, right? So that 3 will come up, and that makes sense because if we did the derivative of x cubed, we would drop it to x squared, right? So we're looking at x cubed being my derivative function, but here's the question. What would happen with the rest of them? Why can we not tack down which one of those 4 is my actual answer? They'll all have the exact same derivative function because they all have different constants, making them all different functions, but they all have the same derivative. They're all the same initial parent function of a cubic function, but they've all been moved vertically, but just different amounts. Therefore, we cannot actually fully define what the function is here, what the original function is. So we use dy, dx, and y or y prime notations for this. Because until we know all aspects of the original function, including that constant at the end, which we are going to affectionately call plus c, you cannot state whether or not you know it is a function because it's not complete. Does that make sense? We will build up to that level of being able to use our function notation. We will talk about how we will fill in all parts of it. It's not that incredibly difficult, but it does require us to use a little bit more math. Questions here before we move along? So, what we will use instead is we are going to use capital F. Capital F instead. Not lowercase s, but capital F. And that is going to stand out to us as this is our antiderivative function. It is not guaranteed to actually be the function. It is just the antiderivative with this unknown c at the end. We believe c is some constant. It could be anything. It could be 0, it could be 1, it could be any number we choose, any decimal we choose, but it is a constant. And it is unknown until tomorrow. Sometimes it remains unknown indefinitely. It depends on the information I give you to start the problem. We call these indefinite integrals because of that, because until I give you more, you have no idea what it definitively will be. Are we all set here with, what is it, slide 4, right? So, let's go ahead, let's practice this giving the antiderivative of some basic functions. So let's start with our first one here. We have dy dx of 2. So, what does this tell me? What would be my original function? What is the antiderivative here of this?
2x.
2x, right? Because if this is our derivative, that means that we started with a 2x, right? Because the x is no longer here. For us to get a constant as a derivative, we must have had a linear function to start with, right? Now, you told me 2x. That's wrong. That is 2x plus c. If you do not put plus c, I will take off points. Until you know what it is there. Questions? Okay, let's try the next one here. We have our first derivative. We have here 4x cubed plus 125, okay? What is its antiderivative function?
X to the 4th plus 125, x plus c.
Okay, are we all clear with Bianca's logic here? We see something with an exponent here. If we see x, then we know that a power rule was used to get here, right? So if a power rule was used to get here, that means that that coefficient, that multiplier, used to be my exponent. Now, maybe it had something else out in front. It could have. But since we know that this one is only one less, we know that this was a standard x to the 4th function. That makes sense. If I would go backwards, right, I would get the initial function again, right? Likewise, 125x and c. Are we all okay so far? Are we all comfortable with this? Okay. Let's go ahead to our last one here. The first derivative of fx, we have 8x minus 3x squared. How are we going to do this one? A little bit more complicated. Jake, you got an idea?
4x squared minus x cubed plus c.
Absolutely. So here's something that we're going to talk about in just a second. But when you see this x, you know the antiderivative, the power rule itself is to subtract 1, right? So if we're going to go backwards, you need to add 1 to these exponents. So if this is going to become x squared, you know that that 2 would come down and be a multiplier, right? So whatever this new power is, we're going to divide the coefficient by. So if my new power here is going to be 2, that means my constant, my coefficient of it had to have been 4 to start with. Does this make sense? We'll show a definitive rule of this in just a minute or two. I'm going to show you a bunch of the base rules to start, just like we did with derivatives, because I'm not going to sit here and practice each one with you. Once you wrap your mind around what we're doing, you can kind of think up the formulas and things on your own. Ones that might stand out is like quotient rule and product rule. Those ones might be a little bit more difficult. Doing the chain rule in reverse is a little bit more difficult. And then we have our minus x cubed, and then, of course, plus c. Questions here about this one or concerns for this one? Let's move on here. Let's move on to our next slide, slide 6. So this process is called integration. It is the antiderivative of this. So derivatives lead us backward to integrals. Now, this is what the notation should look like. This is what the notation should look like, is this little symbol right here. The function we're going to do the antiderivative of, and then what we're doing it with respect to. So like we talked about doing derivatives with respect to x or t, right? You guys remember doing those, I hope. We normally do them with respect to our x values. But we did talk back in Unit 2 and related rates about sometimes we had A, B, and C, and then we took derivative with respect to time. Do you guys remember doing those problems? Vaguely? Okay. So we will state what value, what variable we are going to take the derivative, or we took the derivative from. Therefore, when we go backwards, we need to say what value we're doing this in respect to. So this is taking the integral of 3x squared with respect to x. That is how you would officially and formally say that function, this operation. Fun little anecdote about that symbol. Isaac Newton is the one who used that symbol. That's not Gottfried Leibniz's notation, that's Isaac Newton's. And anybody that way back in Math 2, if you wrote your paper on Newton or Leibniz, you would remember that they did not get along. They both are credited as founders of calculus because they both figured it out in about a year's time difference. But that symbol, it has been relatively proven that the reason why Newton chose that symbol is because it was on his house. His blacksmith used it as some type of decoration for like outside his door, so he just chose that to be a symbol. It has no other real value or meaning. It's not an ancient Greek letter like most of the other things we use. Newton just picked it because it looked cool, I guess. Once again, see my previous notes and statements of mathematicians are lazy. If I need a new symbol to represent something, I'm just going to look around until I find something, and there we go. Good enough. Questions here? All right, let's move on to our next slide here, slide 7. These are some basic rules here for us. These are some basic rules here. So the first one is the one just talked about a little bit ago, the constant rule. If I have just the number, then the previous state of it was that number with x. We discussed briefly the power rule just a minute ago, right here. So what we're going to do with our reverse of the power rule is we're going to add 1 to that exponent, and we would divide the whole thing by that new exponent. So looking at this here, the integral of 8x with respect to x would become 8x squared over 2, which is what gives us our 4x squared. That is how you should set that up. And I highly recommend that as these get more difficult, you take the time to write out that little fraction. This is easy right now. It won't be for long, as this is AP Calculus. I do highly recommend you get comfortable writing that, because when I start mixing these into fractions and everything else, this can become quite complex. Okay? Anytime you have a multiplier out in front of your function, just like we've removed it from derivatives and then multiplied it back in, of course, you can do that in reverse. If I have a coefficient, I can, of course, remove that coefficient and bring it back in. So looking at like this 8x, I could have just treated it just as though it said just a regular x and made that x squared and then brought our multiplier back. And sums and differences, just like you can break up a derivative over addition and subtraction, you can break up an integral over addition and subtraction. You cannot do that for multiplication and division. Questions here? These are some basic rules. These are ones that we are going to apply and work with today. The quicker we get these done, the faster we get these done, the more likelihood that we will be able to go outside today. And it's really nice outside, so I'd like to be able to do that. I had my Math 2 kids outside last period. Let's take a look at the next page here. Next slide. Just a few more ones for us. This is, of course, the opposite of our trig rules, which, honestly, those are just the same thing, just reading them instead of how you had them before. You're just going to flip the idea around. So sine will get us back to negative cosine. Cosine will lead us to sine. Secant squared will lead us to tangent. Cosecant squared back to negative cotangent. Secant tangent to secant. Cosecant cotangent to negative cosecant. The only thing I encourage you to be careful with there is, of course, the signs. Make sure that you're careful with your negatives there. Be careful with your negatives there. Some people do struggle with these because they think sine and they think immediately cosine, but you have to remember that we are actually working the cosine rule in reverse. Cosine spits out a negative sign. So if this is a positive sign, that means cosine had to have been negative to start with. Does that make sense? Just be careful with those signs there. You really just got to be cautious with those. This was, last year, a really difficult test for the AP Calculus students, as was our Unit 3 test was a really difficult test. I don't think the Unit 3 test is going to be any easier that you have your notes with you. I gave them their notes last year and 2 days to do the test, and I still destroyed them. Now, when it came to the Unit 4 test, that was literally the last thing they did before we went on COVID. Like, I'm talking like, we left for parent-teacher conferences, right? Like the day before. Okay, so that Tuesday and Wednesday, they took the Unit 4 test. It was the last thing they did. We started a brand new unit online. It was very weird. But Unit 4 test was a struggle for them because they had to memorize all these formulas. I did not give them a cheat sheet or anything else. So I think that you guys will have a little bit of an advantage there because you won't have to have them memorized. I do highly recommend having a very good command of them so you can spit them back off quickly. You don't want to have to always dig through your notes to find them. If you think that you're going to struggle with that, make yourself a cheat sheet at the last page of your notebook. Make yourself a little formula cheat sheet back there with your quotient rule, your product rule, some of your limit stuff. Put these back there. That's what I would do. Start making my own AP Calculus cheat sheet. It will help you out with your AP test sometime in May. I recommend doing that with like the last page or two of your notebook. That way you know quick reference where it's at. That's why it's always the last pages in a book in the first place. In your calculus book, I believe it's the first pages, actually. No. It's the last pages in the book. Where is it? Oh, there's a couple of pages where it's just formulas. It might be the last few pages. Nevertheless, not relevant. Dig through your book, you'll find it. Okay, let's move on here to our next slide here. So slide 9, let's get into some last minute things. So rewriting your integrals is extremely helpful. This works really well with the fractions and roots, as the roots have been given us fraction derivatives, right? So just as we rewrite those, I definitely think you're going to want to rewrite them before you do the integral. So if you have something in a fraction form, rewrite it. If you have a root as your, before you do your integral, rewrite that as well. I really, really, really think that that's going to help. I would also say in that setting, if you are taking a fraction and rewriting it, if you're taking a root and rewrite it, I recommend moving any coefficient out and putting it back in after you have done your reverse power rule. That is my suggestion. Of course, you don't have to do that, but Mr. Kaufman's been doing this for a little while now. There's a method to my madness. I suppose you'll have to either find that method or create your own. Are we all set before we move along with slide 9? One more second, okay. I'm pretty sure from here out, we're going to be looking at just doing practice problems. Just doing practice problems. I don't have many slides here today. Yeah, just practice pretty much from here out. Varying types of practice, I should tell you. Varying types. We have a couple of different types of problems we're going to look at today. We're going to go from all scales from easy to difficult. If we can finish them before time runs out, we'll go outside and we'll work on some more practice problems I have for you. Are we ready to begin? Okay, here's 3 of them. Let's find the integrals. Here's 3 of them. Let's find the 3 integrals. Gonna walk around, take a quick peek, but these should not take us very long. These are 3 very easy ones. Trying to baby step you into this before I just throw you into the deep end of the pool. I don't like what you've done. You have not done the whole power book. That looks good, except for you're missing something. What are you missing? Grab my rusty colored pencil here. Come around, let's mark some people's work. Pretend like it's a quiz, let's pretend like it's a test. Okay. Let's go write it down. Is that all right? Are we finished with it? No, we're not. I recommend taking and rewriting that before you try to do the integral. Rewrite that as x to the negative third. That is not our power law.
For the first one?
That's not the reverse of power law. That is not correct. This one was. Now we can figure out the 2 of this. What we got? X to the negative what? Add versus negative, right? X negative. Okay. Plus the dot. Check on our last few here. Who would like to help us get started? Feeling confident about any of these? Mr. Pam? Which one would you like to do, sir? The first one, okay. What did you do?
I used one of the rules.
I think the first thing we should do, Colin, is rewrite it.
Yeah.
Let's rewrite this so that way it's x to the negative third dx. Okay, now let's take the antiderivative. So let's use the rule you were talking about. What are we going to do?
Use the formula x n plus 1 over n plus 1.
Just like this. Colin, let's redo a little reduction here. X to the negative second over negative 2 plus c. Yes? And then, of course, the last thing we need to do here, negative 2x squared plus c, correct? This is our antiderivative function, so capital F. Are we all okay with what Colin and I have done? Now, you don't need to have all of these steps, but I do expect to see some of them. If you are simply just going from integral to answer, I am going to mark it wrong because it has no work. While some of these, yes, you can do in your head once you get good enough at them, I expect you to show some level of work. Who wants to help us out with another one? Jake and Bianca. Let's be gentlemen. Jake, Bianca, which one would you like to do?
What is the second one?
Do the second one. Okay, what'd you do, Bianca?
First I took out the 2.
Separate the 2 as a multiplier, so integral sine of x dx. Very good.
And then the integral of sine x is negative cosine x plus c.
So we have 2 times negative cosine x plus c.
And then you distribute the 2 out. So you have negative 2 cosine x plus.
And that's going to remain plus c. Because it's a constant in the first place, we'll just change whatever the constant is. It's an unknown. So I'm not going to write 2c. I'm just going to keep it as c. Okay? Questions here? Concerns here? This is good for our antiderivative here. Jake, can you help me out with the last one?
So the 3x and then the power 1 plus 1 over 2.
So you went right to the power rule first?
Yeah.
Okay, just want to make sure. So we have 3x 1 plus 1 over 1 plus 1, correct?
Yep.
Okay. This gives us what, Jake?
3x squared over 2. Plus c.
Plus c, thank you, sir. That is, of course, our answer. Now, Jake, I wanted to clarify, just because you could have did what Bianca did here, you could have separated that 3 away, just to show a slightly different alternative take. Could have said 3 and then the integral of x dx. And then 3, you would have had x plus all over plus c. And you would still get the same answer. Make no mistake. Make no mistake, you still get the same answer, just a slightly different twist on the same problem. And sometimes the way Jake did this is going to work just fine. For some problems, be just great. For others, you're going to want to do this instead. Okay? Questions here? Issues here? All right then. Those are my values. Those are my values right there for my answers. Let's go ahead. Let's move on to slide 11. Let's do some more practice problems. Here's 2 more for us. Slide 11. Now look, I'm not going to beg and plead you all to participate today. But if you find yourself not doing well in class, the best thing for you to do you're not happy with your test grades or your quiz grades, the best thing for you to do is to get more involved. I'm not going to beg and plead anybody to participate. It's an AP class. You know what you signed up for. But I will tell you, participate with these examples, whether you are physically here, whether you're on the live stream, whether we are, whatever we're doing, being more active, being more involved will yield a higher and better result. Ready? Let's go. Let's do one. Maddie's gonna do the first one. Okay, Maddie, what'd you do?
You said one. So it's 5x 9 plus 1 over 9 plus 1.
Okay, so Maddie, what we should do here is we're gonna break this up into 3 individual integrals. Because we can do that just like we would otherwise, right? Dx plus 6x to the 8th minus 2x squared dx. Now, you don't necessarily have to show this step, but this is what we're going to do, right? We're going to do each one individually, right? So if you don't show this step, that would be acceptable, but I should see the next step, which is what you started saying. We're going to have 5x to the 9 plus 1 over 9 plus 1 plus
6x 8 plus 1 over 8 plus 1.
If you want to start reducing this without writing the plus 1 all the time, I can accept that as speeding this up just a little bit, because we can all do basic addition and subtraction, yes? So we're going to get 10, 5x to the 10th plus 6x to the 9th over 9 minus 2x to the 3rd over 3, right? And
x to the 10th over 2 plus 2x to the 9th over 9 minus 2x squared over 3 plus c.
This is our antiderivative of the first one. Questions here? Okay, second one, Callie?
I do the power.
Okay,
And then that's 7x 1 plus 1,
2.
2 plus 1. Yeah, and then over 2 plus c.
And that's it. Not really a whole lot of work to show there. Not really a whole lot of work to show there. The only thing you could have done, Callie, differently is you could have separated that 7 out as a constant multiplier. Questions? Onward. Onward. Slide 12. Slide 12. Let's take a step up. Let's take a step up. Nope, it's not a constant. Wow, that's what we've done. Where's your different from? 10. First thing I would do is start by copying it down. Too much work to show for that problem, not to. Too much work to show for either one of these problems, really. Start with the rearranging. I suggest you send that in. That's nice. I would not do it like that. Can't separate it like that. Nope. That's my advice to your groups is to start by rewriting. This pain.
Sorry. Is that how you do it?
Nope.
Okay.
You're on the right track. You're on the right track. I'm not sure if you finished it out correctly. Didn't look that far ahead. But with the first few steps, they're correct. And the rest of this correct, you should be on the right track. What do we got here?
Is that how you start like that?
I would not do that. I like that first step. I would bring it all the way up. Send it through. Okay. First. No. No. Well. It's good. It's all right. Yeah. You don't want my hair. Well, no, actually, yes, you're fine. You're fine. Not that. I don't want my hair. Nope. Nope. I would not make that into a negative exponent. Who's ready to get started? Mr. Kaufman's ready. Who's help us out here? Colin. I thought you might. Colin, what'd you do?
I rewrote it first.
Yep. That was my advice, right? Anytime we got fractions or roots, we rewrite. I'm going to rewrite it as x to the negative 1/2 dx. Now what'd you do, Colin?
I distributed the x.
Absolutely. I haven't taught you how to do the undo the product rule, right? So we're not going to be able to undo it yet. So we have to get to something we can do. So let's send it through. This becomes x to the what? Plus x to the what?
X to the 3 over 2 plus x.
It does not. It becomes x to the 1/2. Because as we multiply, we add exponents. That's why I said I didn't particularly care for yours. Aside from that mistake, everything else on your work was good, but we can fix it from there. And this becomes x to the negative 1/2. Integral dx, right? Okay? So I know that we're going to have to adjust on the fly now, but I think you can handle it. We're going to apply our respective power rules in reverse, yes? Okay, so for our first one, we're going to add 1 to that exponent, making it 3 over 2, and that is what we are going to divide by 3 over 2, correct? Plus, we're going to add 1, we're going to get x to the 1/2 divided by 1/2, right? And of course, plus c at the end. Colin, you want to do a fractions or roots first?
I rewrote it as roots.
Okay, so let's do that first. We're going to have x, this is a square root of cube, right? Plus square root x over 1/2 over 3 over 2. Now let's undo the fractions. We're going to have what?
Square root x to the 3rd multiplied by 2 over 3.
Yep, 2 over 3, or 2 root x cubed over 3, right? Plus
2
plus c. This is our antiderivative function for x. So Colin, I liked your work, even though you made that mistake early on. The rest of your work was in line with what you needed to do. Okay? So just be careful there on that initial assessment. Now, you could have done it a little bit differently. Instead of doing the negative rewrite, you could have separated them into 2 fractions and then subtracted your exponents. That also works. You could have split this up rather than doing it this way. You could have split it into 2 separate fractions and then subtracted your exponents. That would have also worked. You get the same answer. Okay. Anybody want to try? This one in black. No? Why not? What's wrong, guys? Colin. Take someone. Yes. Who are we throwing onto the proverbial train tracks? Bianca. Bianca, what all have you tried so far?
So far, all I have is I moved the cosine squared up.
I would not.
Great.
I would not. That doesn't help us.
Yeah, I noticed.
Doesn't help us. Because as opposed to the previous one, we can't really distribute that. So we're stuck right now, right? Okay? So let's try something else. What was the other way we could have did this one? I told you should split it up into 2 fractions, right? You think that'd be helpful? Okay, so let's split the cosines. If we split the cosines, we'd have sine over cosine. And we're going to have 1 over cosine. dx. Okay? What can we do with these?
You can turn the sine over cosine into tangent.
Okay. What can I do with 1 over cosine? What does that become?
Secant.
Yep. Okay. Now what?
Now you just use
The rule. The tangent secant rule. What is it? What's the antiderivative here? I just had it up there just a minute ago. What was it? You got your Chromebook open. I'm sure you got slides somewhere, right? Go back, find it. What is it?
secant x plus c.
Not just secant x.
Plus c.
Plus c. Questions here? Concerns here? So out of the 2, I actually think this one's a lot easier. But you got to apply a little different problem solving to it. This is why I said on the live stream that they should absolutely be trying these with us and not just listening to us do them, but actually physically writing them out themselves. This is part of the reason why we're practicing this today. Ones like this, where you have to do a little bit of manipulation to get it going, can get tough quick. Let's move on. Let's move on to our next set here. Next slide, slide 13. How to find C. How to find C. So if we are going to find C, we need some more information. Told you I didn't give you enough. Now I'm going to tell you how you can do it. Okay? So there's a couple of ways. We can have some points we need to plug in and evaluate, or we can have a little bit of information about the starting function from the beginning. So if I give you enough starting information, enough about the original function, the original fx, you can use that to help you find the value of C. If you know, for example, an x and y points of the original function, you can use that into these antiderivatives to find any constants that might be attached. Does this make sense? It's very similar in concept. If you go all the way back to math 1, how like sometimes you get the slope and a point, and it would ask you to write out the line, right? So you'd have to plug in the m, plug in x and y, and find b, right? So this is very similar to that idea that I give you enough to get started to finish it out. Questions here? So I have an example here for this first slide. I have my derivative. My first derivative is y equal to 3x squared plus 1. and we are going to pass through the point 2, 4. Now, I cannot really make it much more explanatory than this example. I'll walk us through this one just so that way we all feel confident in what we're about to do. So we're going to begin this by the same process that we have been practicing today. We're going to find the antiderivative first. So I'm going to start with my 3x squared plus 1. We are going to take the antiderivative or the integral with respect to x. This is going to become 3x to the third over 3 plus x. The 3's cancel, and I have x cubed plus x plus c. Are we all okay here? It's my antiderivative function. Now, we have an x, we have a y. We're going to take that x, we're going to take that y, we're going to plug them in. We know that when I plug in 2, I get back a y of 4. So very simply, we should be able to solve this down from here. This is going to be 4, 8 plus 2 plus c. That gives me c equal to -6. So I have found my c value, which means that my true original y function, my f of x function, now we can use this notation because we know definitively what function we are dealing with, full, free, and clear, is x cubed. Why did I choose to write that there? X cubed plus x minus 6. Now I can absolutely go down and use that notation. So if we finish clicking our way through, we have our capital Y is the way I would use that if I don't want to use capital Fx. I would use a capital Y to represent the antiderivative. I plug in, I solve, I get -6. So now I know without a doubt what my function truly is. Questions here? It's just doing the antiderivative with just a follow-up step. Isn't that complicated? It's not a big leap mathematically, concept-wise, from what we are doing. Are we ready to try 1 or 2 on our own? Awesome. Let's go on to slide 14. Can you do this one without me? Go ahead. If we can put the pedal to the metal here, ladies and gentlemen, we might still be able to make it outside, but it's unlikely as class is over in 15 minutes. Took a little bit longer going through this than I thought we would. Does anybody want a physical copy of the study guide that has some extra ones? Anybody else want a hard copy of the study guide? One left? So. The extra work that we were going to do today is a solution for it. It should feel like you need more practice. The extra work we were going to do today is a solution for it because you need more practice. And extra work, solutions, not required, but recommended. Same drill, extra work, answer key, in case you want to try a few more. I will see you. Don't push yourself to try to get this extra stuff. This is not all. This is just extra probably work. Extra work in the answer key. Should you decide that you want to try something else. Okay, you earn that shirt. 2 x to the 4th plus 5x. That will be 1. And we get back. A few more steps along the way. I know you're doing a bunch with your head, but 1 or 2 more steps along the way here to help ensure that you make a mental misstep. I don't take off the full plan, I take off half. I'm not saying there's anything wrong.
No, just what's the?
Well, like, right here, you didn't actually state what the antiderivative function simplified was.
Oh, okay.
Right here, you can go right to plug in, right to answer. Maybe 1 step in between for each of those, okay? All right. We should be just about done here. Who'd like to help us out? Callie's going to do it. Callie, walk us through what we did here.
I did the column first time derivative.
We got our integral 8t cubed, right? Plus 5t with respect to t, right? Now, some people switched over to the x. That's fine. It's not a big deal. But just make sure that you, if you switch in this, make sure you put d to the correct variable there. Okay, what do we got for our antiderivative function? Let's start with that. How do we start that?
I did 8x 4 to the 4th over 4. 5x. And then plus 5x plus c.
Okay.
And I simplified to 2x to the 4th plus 5x plus c.
I do recommend writing out this simplified antiderivative. It is going to be one of the checkpoints I'm going to be looking for on your work to make sure that it is correct. What did you do from here, Callie?
And then I plug in 1 to the f of x, which is equal to 4, and solve for c.
It's going to give us 2 plus 5, 4, right?
Negative 4.
Negative 4, yes. Sorry. Plus c. That's all.
And c is equal
Keep
to
me honest. I like it. Make c
11.
negative 11. And then we can write our actual formal function here, f of x or f of t. In this case, it's actually h, because it does say h of t up there, right? Would be
2x to the 4th plus 5t minus 11.
questions here. Now, I'm going to take off points, but I have been told that the College Board Calc test is particular enough that they would have HX and HT, and HT would be the correct answer. So do be cautious with that. That was told to me. I don't know if that's 100% valid or not. I've never seen a question like that on their prep materials, but I want to put it past them either. Comfortable here? Awesome. Awesome, awesome, awesome. I have the last one here for the day. Little bit of a challenger problem for you. A little bit of a challenging problem for you. I have there the second derivative. Go ahead and see if you can figure this out. Go ahead and see if you can figure this one out. Get the answer. I have to say, I'm actually getting a little bit excited. You see, the most I taught last year with calculus up through Unit 5. We're definitely going to get past Unit 5, so we'll get on to some things that Mr. Kaufman has yet to actually practice teaching once before.
So we have to like solve it for each derivative, because like, yeah.
A couple of you guys look like you're finished writing. A few of you still working. Do we need another minute, or are we ready to go? Gang, do we need another minute, or are we ready to go? Ready? Ready? Okay, then let's go. Who wants to help us? Gotta help us out. Okay, first thing we're gonna do, very clearly, as I already have it up here, we're gonna start with taking the first integral, right? Okay, so what are we gonna get here?
I got x cubed over 3 plus c.
And if you want, here's what I would do is I write capital F, but I will put the first derivative marker on it. Because this is not the antiderivative function, it's actually the derivative of the antiderivative function, right? And then what did we get from here? What did we do?
It gives you that your f derivative of 0 is 8, so I set that equation equal to 8. 8 equals 0 cubed over 3 plus c.
Which makes that pretty easy. That makes
c
c
equals 8.
8. Okay, so that helps us actually write the first derivative function, right? Definitively, we know it to be x cubed over 3 plus 8, right? How does that help us? What's the next step?
Now you can find your actual integral, which
We'll pick up the first derivative and go back to the true antiderivative here, right? Now, when we set this one up, how'd you approach this? There's an easy way and a hard way.
I took out the 1/3.
I think so. I think that removing that 1/3 multiplier makes this a much easier power rule to do rather than trying to do it as it's already built in.
Yeah, and then I got
This gives us 1/3. This will become,
x to the 4th over 4.
which is going to be much easier to simplify, and plus
8x plus c.
8x plus c. And this is our true antiderivative function right here, which, of course, we're going to do what with it now? Well, I guess we can go ahead and simplify it, right? X to the 4th over 12 plus 8x plus c. Now what?
And then you set that equal to 0 and set your f of x equal to 4 and your x equals 0.
Now, Mr. Kaufman was kind and chose 0 to be put in just for your benefit, really, because I knew that there's a chance that we might run out of time, which we are running low on it, to make this relatively quick simplify. I would highly, highly doubt that I'm going to do this on a quiz or a test, because I would expect you to actually plug these numbers in. Bianca, what does that make our actual equation here then? What is our fx equation?
X to the 4th over 12 plus 8x plus 4.
There we go. There we go. Questions or concerns about this one? Excellent. Excellent, excellent. Well, we're just about out of time. So if we want to go ahead and start packing up, that's fine. And we'll go ahead and end our live stream. Hope everybody's doing well there. If you have any questions, make sure to shoot Mr. Cochran an email. And we'll get